This next question is something I got asked about in tutorial. It's probably a little more basic than what I've talked about in the other videos, but I think if you're new to dealing with vectors, it's probably a good example to kind of get your head in the space of, one, thinking about vectors in terms of right triangles, and two, thinking about vectors in terms of x and y components. It's a handy trick of the Cartesian coordinate system that if I have a vector that's partly in x and partly in y, I can decompose this vector into some x part and some y part. So let's call this vector v. This would be vy, this would be vx. Now really these should be centered at the origin, but I just drew them a little off the axis so you could see what was going on. If I know this angle here, theta, then I can always say that the x, think about this, x is adjacent to that angle, is v cosine for adjacent theta, and vy, y is, if I move that vector over opposite, v sine theta. So let's use the idea of a vector, and notice that these two x and y components, so if I draw them somewhere else, so this was my x component, this was my y component, that these make a right triangle if I fill in the original vector. And that means that if I didn't know v, I could do v equals the square root of vx squared plus vy squared, simply the Pythagorean theorem. So let's take this principle, the sidebar here on the example, and apply it to forces, since that's what you've been talking about. So I'm going to have a block, and we're going to look at the block from the top. So this is like if I were standing above the block, looking down. There are going to be two force vectors on this block, and they're going to be the same size, F naught. And we're going to know that for this block of mass m, the force F naught causes an acceleration of 17 meters per second squared. Now I wrote this in the form of Newton's second law. Force and acceleration, especially if we're talking about net force and net, or well, acceleration, are related by mass. So if these two force vectors, each on their own, so if I just had this one, this would cause an acceleration, let's call this a naught. And if I had just this one, it would cause an acceleration a naught. What I want to know is if I applied both of them at the same time, what would the acceleration be? Before we do this with the Pythagorean theorem, because you should already kind of see the mapping here in your head of how these two things would work, let's think about what direction this would be. Now, when we add vectors, so it's this vector plus this vector, the way to do this is to pick them both up in your head. So I'm going to grab both vectors. And I'm going to put one down anywhere, but the rule is I can't change the direction it pointed. Just got to pick it up and put it back down somewhere else without rotating it. So here's vector 1. And that has magnitude a naught. Then I pick up the other vector. And I'm going to put it down so that its tail is at the tip of the first vector. Give me just a second here. I dropped my pen. So why don't you try to write out what you think this would look like if I put down this vector with its tail at the tip of this one. Try that either on paper or in your head real fast. And then to find the resultant vector, so which way this thing is net getting shoved, I just take the tail of the first and connect it to the tip of the second. So this is my overall acceleration. But now, how about if I want to know how big a net is? Well then, we're just taking this equation and using our a's. So a equals the square root of the xa, which is a naught, squared, plus the ya, a naught, squared. Now, you might think, well, do I need to worry about whether this is positive x, positive y, negative y? Notice these are squared. So no matter if I put a positive or negative, I'll get the same answer. That means that this equation cannot possibly tell me about direction. It can only tell me about amount. So the amount is going to be 17 meters per second squared. 17 meters per second squared, all into the square root. And if I work this out, I get 24 meters per second squared. Now let's pause and think about this. there's a rule that says the hypotenuse of a right triangle must be bigger than either side, but smaller than their sum. So that means this has to be bigger than 17, check, but smaller than the sum of the two sides, 34. So I had someone in the tutorial show me an answer and say, is this right? And I said, well, I don't know, but it's not obviously wrong. And the way I checked was, is it bigger than either side and smaller than the sum? So that's just kind of a rationality check to know if you're in the ballpark. Now let's try something a little bit more difficult. What if I don't put these two at right angles? So these two are at right angles. What if I don't give them to you like that? Instead, if we have one vector that points just in, let's call this negative y, and another vector that points at 45 degrees from that one. And we'll have this one be 2 f naught, and this one be s naught, which means this one by itself would accelerate at 2 a naught, and this one by itself would accelerate the block at a naught. Well, this doesn't quite make our nice right triangle, but if I split this up into an x part and a y part, then these two will just add in y, and this one will be our x. Another way to think about that is the net x force is just this one, which you could go ahead and figure out. So x is opposite on the triangle. So this would be f naught, sorry, opposite sine, 45 degrees. And for y, this would be the original 2f naught plus f naught cosine 45 degrees. And I said I wanted this to be negative y, which I'm going to use to prove a point here in a second. So let's have these be negative y. And then this just translates into a naughts, or a, because we're going to have a net x acceleration and a net y acceleration. You might be confused about where this is going. So let me move forward, and you can see what happens. So let's talk about the sum of the accelerations from these vectors in y. So in y, we get 2 times f naught, and we still call this negative, so negative 2 times 17 meters per second squared, or a naught, because we know f naught would cause an acceleration of 17 meters per second squared, and we called that a naught, plus negative f naught, or replacing it with a naught, cosine 45. And if I just go ahead and do 17 per second squared, cosine 45, and the sum accelerations in x is just this one, which is 17 meters per second squared, sine 45 degrees. And now I can do the actual math behind this. Sum ay equals negative 34 meters per second squared minus 12.02 meters per second squared. Sum x equals just this, which turns out to be 12.02 meters per second squared. Well, now think about what I've done. If I draw this on a Cartesian coordinate system, y, x, then this sum of ay is the total pointing this way, and the sum of ax is the total pointing this way. So I've made two new vectors, ax, ay, from these two vectors by adding up the y parts and adding up the x parts. Well, now that we're back to the right triangle. So I could find their direction, and I could find their magnitude just by saying that my overall a vector, and remember, This equation can't possibly tell us about direction, so it's a mistake to try to put a vector hat there. Of AX, 12.02 meters per second squared, all squared, plus this amount, negative 36.02 meters per second squared. Well, because this is squared, that negative doesn't matter. I get out my overall acceleration is about 46 meters per second squared. So hopefully that helps. I probably dragged this problem out a little more than it needed to be, but I wanted to make sure you got the ideas of visual vector addition, tip to tail, using the Pythagorean theorem, but only if you can get the vector components so that they form this nice right triangle.